Uh, I I guess it's there's enough air gaps where it gets denser. But if you've seen concrete roads, they have those expansion gaps.
So
If you go to Orlando, those concrete roads have strips in the expansion gaps.
So does it depend, like, kind of on the material?
Yeah.
basically?
So, as a material scientist, you would do all of that. Okay. Global warming will produce rising sea levels, partly due to melting ice caps and partly due to the expansion of water as average ocean temperature rises. To get some idea of the size of this effect, calculate the change in length of a column of water 1 kilometer high for a temperature increase of 1 degree Celsius. Okay, so global warming, as you know, I mean, in the 1800s, the average Earth temperature was 14 degrees Celsius, surface temperature. Today, it's about 15.5 degrees Celsius. We were trying to be below that, but that goal is gone. Now we were trying to be below 16 degrees Celsius, but that's also ain't going to happen. So, so here's the ocean. The ocean depth, average depth is 4 kilometers. 4 kilometers is from here to the beach. For a temperature increase of 1 degree Celsius. So assume the column is not free to expand sideways. So all the expansion is happening in this direction. Okay. So the length of the column is increasing. Alpha times L times delta T. So volume expansion coefficient for volume expansion coefficient for water. So that's another thing your calculator couldn't have done. She didn't hear me. Okay, so remember alpha is 1/3 of beta. Okay, so that's 70 into 10 to the minus 6. So the increase in length would be one kilometer is 10 to the 6 meters, not 10 to the 3 meters. And 1 degree rise in temperature. About 3 inches. Okay, so every degree rise in temperature would increase the ocean height by 3 inches. So the expansion is not that big an effect. It's the water flowing in that's the big effect. If you go to Matanzas Inlet in near St. Augustine. During the ice ages, the water level was, okay, so if all the ice in the world melted, that is Antarctica and all that, the water levels would rise by 65 meters. During the peak ice age, the waters were 100 meters below current levels. If all of Greenland ice melts, the sea levels would rise by 7 meters, twice the height of this room. Okay. So the same heat transfer into identical masses of different substances produce different temperatures changes. Calculate the final temperature one. So you saw that, that's how. So for breeze to happen, for any breeze to occur, so if you want a breeze, horizontal breeze, what do you have to have? High pressure here, low pressure here. How do you get low pressure here? This has to warm up. So differential heating is what gives rise to all breeze. Okay. So if you have a parking lot and a meadow, the parking lot gets warmer, it gets low pressure, you'll get breeze from a meadow to parking lot. All right, so that's sort of what this thing is related to. Calculate the final temperature when 1 kilocalorie of heat is transferred to 1 kg of the following. We'll do water and concrete, okay? So 1,000 calories. Oh, well, so and 1 kg. And the specific heat of water is 1 kilocalorie. Calorie per kg per degree Celsius. So it's 1 calorie per gram per degree Celsius, and so okay. So the temperature rise of water would be 1 degree Celsius. Now what we're going to do is, so if that heat was falling on a lake, the temperature of the lake water would rise by 1 degree Celsius. Now let's put the same amount of heat on concrete. And the specific heat of concrete specific heat of concrete. Okay. 880 joules. Okay, so specific heat of concrete is about 900 joules per kg per degree Celsius or Kelvin. And we want to convert this to calories, so uh, 200 calories per kg per degree Celsius to 0.215 kilocalories per kg per degree Celsius. Okay, so you can see that the rise in temperature for concrete will be about 5 degrees. So when the water temperature rose by 1 degree Celsius, the concrete temperature rose by 4.56 degrees Celsius. Okay. So that's how you generate breeze. Again, differential heating. So for instance, so here's a so the earth is spherical, you're getting sunlight, and you see this amount of sunlight is spread over a larger area. At the equator, it's spread over a smaller area, so this gets warmer than that area. Now, if the earth were flat, what would happen? You wouldn't have weather because everything was getting heated equally. And it turns out that you have seasons because the axis is tilted, and different times of the year your angle of inclination is the same. If the axis were not tilted, then you would have the same weather all year round. To the Okay, so this problem says, following vigorous exercise, the body temperature of a 80 kg person is 40 degrees Celsius. Apparently, if your body temperature gets to be 42 degrees Celsius or something like that, around there, that can be fatal. Yeah. So you want to cool down fast. Your normal body temperature is about 37 degrees Celsius. Okay. At what rate in watts must the person transfer thermal energy to reduce the body temperature to 37 degrees Celsius in 30 minutes? So you're going to cool down to normal body temperature in 30 minutes. Yeah. Assuming the body continues to produce heat at the rate of 150 watts. Okay, so you got to make some assumptions. What are you? A person is just really a bag of water. So we'll assume the specific heat of water. Okay. So the amount of heat you have to lose is mass of the body. So that's 80 kg person. Specific heat times the temperature. Okay. So the amount of heat you have to lose is 80 kgs, and the specific heat of person is 1 kilocalorie per kg per degree Celsius. So that's how much heat you have to remove. And how much do you have to cool? 3 degrees Celsius. So this is how much heat you have to remove. So that's 240 kilocalories of heat. And you want to, so how much time do you want to remove it in? 30 minutes. Calories. And joule conversion is 4.186 joules per calorie. 30 minutes is that many seconds. Okay, so that's the rate at which you have to remove to cool the person down by 3 degrees Celsius. $558 Okay. Well, so, but you're also producing this heat as for your normal functions. Okay, so your cooling rate has to be, the net cooling rate has to be 558 watts plus 150 watts. That's 708 watts. Okay. So your cooling system has to increase by a factor of 6 or 5. Did you guys understand that? A 1.2 kg sample of water at 10 degrees Celsius is in a calorimeter. You drop a piece of steel, so we'll do this experiment. You drop a piece of steel with a mass 0.38 kg at 215 degrees Celsius into it. What is the final equilibrium temperature? Okay. Okay, so the steel loses heat, mass of steel times the specific heat of steel times final temperature minus initial temperature. So the final temperature of the steel is less than its initial temperature, and so it loses heat. This will be negative. And the water gains heat, specific heat of water, final temperature minus 10 degrees Celsius. And this should add up to 0. The heat lost by steel is equal to the heat gained by water, and they should add up to 0. So final temperature is MSCS T initial plus MWCW times 10 divided by MSCS plus MWCW. So there's the specific heat of steel. mass of steel was 0.385 kgs. So the final temperature is 16.4 degrees Celsius. So let me point something out. So look at this. You drop the steel metal of 215 degrees Celsius into 10 Celsius of water, and the final temperature is 16 degrees Celsius. See, that's the effect of the high specific heat of water. The water temperature changed only by about 6 degrees, and the temperature of the steel changed by 210 degrees. 200 degrees Celsius. Okay. The masses are slightly different, but still, it's the specific heat. The specific heat is 10 times greater for water. Yeah, about 10 times greater. All right, so let's do these backwards. Okay. What is the rate of heat conduction through 3 centimeter thick fur of a large animal having a 1.4 meter square surface area? Assume that the animal's skin temperature is 32 degrees Celsius and the air temperature is minus 5 degrees Celsius. And that fur has the same thermal conductivity of air. So the reason we assume this is all animal furs have these thin, fine hair which are trapping air. So that's why you assume the thermal conductivity of air. Okay. This is some animal hibernating. Okay. So the rate of heat flow, remember Q by T is thermal conductivity by area times the temperature difference, I minus temp, divided by the thickness. Okay, so animals when they're hibernating, you're not eating anything. You want to decrease the rate of heat loss. What is the thing you can do? You can try and reduce this number. So you go structures hair such that you trap air. So this thermal conductivity is decreased. If you had just blubber, heat would flow out faster. Okay. What else can you do? They do the following. This number can be reduced if this number is smaller. So they lower their body temperature during hibernation. See, the body temperature is decreased from 37 degrees to 32 degrees Celsius. What other advantage is there when you lower the body temperature? Your metabolic rate has gone down. The amount of energy consumption has gone down. So all animals know physics. Okay? Biology knows physics. Okay? All right, so we'll just calculate the heat transfer. So Q by T, power, is thermal conductivity of air. Okay. What would we do without ChatGPT? Thermal conductivity of air. Okay, so watts per meter per Kelvin. Area is 1.4 meters square. And temperature difference is 32 minus of minus 5 plus 5. And the thickness of the 3 centimeters. Okay, so the meter square cancels, the kelvins cancels with the Celsius. Okay, 1 degree Kelvin is the same as 1 degree Celsius. I mean, not the absolute value, the difference. Okay, so this is 2.6 times 10 to the minus 2, that'll kill that. So that is equal to 2.6 into 1.4 into 37 divided by 3 watts. See, you have, how much heat are you losing a second? 100 joules. You're a 100-watt bulb. That's how you remember it. You're hibernating, and now you become a 50-watt bulb. Yeah? All right, we won't. So that's the important part, and that you guys can. Yeah. It is difficult to. Oops. It's difficult to extinguish a fire on a crude oil tanker because each liter of crude oil releases that many joules of energy when burned. To illustrate this difficulty, calculate the number of liters of water that must be expended to absorb the energy released by burning 1 liter of crude oil if the water temperature rises from 20 to 100 degrees Celsius. So this is the ocean temperature. It boils, and the resulting steam temperature rises to 300 degrees Celsius at constant pressure. Okay, so what we're going to do is you're going to burn 1 liter of oil. So this is a fire, and how much it releases that many joules of heat. And you're going to use this heat to raise the temperature of water then convert it into steam, and then heat the steam. Okay. So we'll calculate this, the mass of the water is, all this mass is the same. So the mass of the water is the amount of heat divided by CW delta T plus L plus CS delta T. Okay, do you guys understand mass of water equal to mass of steam? Okay. So this is the amount of water you would need to absorb all the heat released by the oil, burning oil. Okay, that's what that means. All right. Specific heat of water is and you're heating water from 220 to 80, 100 degrees Celsius. So the rise in temperature of water is that. The latent heat of vaporization of water, the latent heat of vaporization of water is 2.26 times 10 to the 6 joules per kg. See, this term is joules per kg. All the denominator terms are joules per kg. And plus the rise in temperature of steam is, steam goes from 100 to 300 degrees Celsius. Specific heat of steam. Specific heat of steam. So the specific heat of steam is 2000 joules. See that our water is more than twice that. And the rise in temperature of 200 degrees Celsius. Okay. All right, so let's do this. Okay, so the mass of water you would need to absorb that is 9.35 kgs. And the density, density is mass divided. Nine 9.35 kgs, and the density of water is 1 kg per liter, so 9.35 liters. So to put out the fire from 1 liter of oil burning, you need 10 liters of water. And that's got converted to steam and stuff like that. And here's the problem. When oil gets on the ocean, it spreads out. Okay, so you're spraying water. You need 10 times the water, you know. So those fires are hard to put out. So what do you do? Huh?
Don't use water.
So how do you put out that flame? So whenever you have trouble, and you have trouble if you want to put out the flame of a lithium-ion battery in electric vehicles, you cut off the supply of oxygen. So you spray with foam and whatnot, and you do that in many, many places. Okay. All right, I'm going to do just one part of this problem and then we'll be done. Okay, so you've heard of many icebergs breaking off. And the question is, how much heat is needed to melt these icebergs? And where is that heat coming from? I mean, it comes from the warm ocean waters and sunlight falling on them. Okay, this asks you the time, but I'm not going to do this. I'm just going to do one part. In 1986, and I believe that iceberg is still around, an enormous iceberg broke away from the Ross Ice Shelf in Antarctica. It was approximately a rectangular prism, 160 kilometers long, 40 kilometers wide, and 250 meters thick. Okay, so 250 meters, 40 kilometers, and obviously this is not to scale. Okay, so the mass is density times volume. Yeah. Density is 917 kg per meter cube. Okay, to give you a sense for the size of this ice cube, DeLand, Daytona, Jacksonville. And the height is the same height as 5 of the tallest buildings in Daytona. 5 of the tallest buildings in Daytona. So that's how big the ice shelf was. And you're going to try and melt this. Okay, so the mass is that much. And the volume is 40 kilometers into 160 kilometers into 250 meters. So this is 10 to the 4, 8, Okay, 10 to the 4, 10 to the 9, 10 to the 11, 10 to the 13. And 9.1. So the mass of the ice shelf was that. 1,000 kgs is roughly, you can think of it as 1,000 kg is this much water. Okay. So 1 trillion small cars. Okay. All right.